All right, so welcome to a lovely Friday morning. Today's plan, I do want to show you another example of finding center of mass, but this time of a region that's bounded by functions above and below. You'll see that it's not really that different, that the build is pretty much the same. We end up integrating something different, obviously. And then I want to talk about applications that involve exponential growth and decay. So just so you guys are aware in terms of the sections of this book. So we're in the middle of, I think it's section 2.6, which is moments in center of mass. And then section 2.7 is like a review of exponential functions and logarithms. They fill in just a few more kind of technical details, like the fact that you can define the logarithm as an integral and stuff like that. We're not going to go over it because it's exactly the same stuff as you did before. I still want you to do the homework though, because it will help you remember the rules of logs and exponents and things like that. But we're really going to jump into 2.8, which is applications using exponentials and logs. Specifically growth and decay. Okay, so that's what we're going to do today. We're going to do one more example from 2.6 and then dive into 2.8. Anyway, so that's my plan. But as always, what do you guys want to look at? Any homework questions out there that are causing you issues? Oh, that just reminded me. So remember the disk problem where we were trying to find density and there were some issues? So I figured out what the problem is. When they gave us a density, they intended that to be a radial density, where the x was the distance away from the origin or from the center of the circle. I, of course, took it as x is a density in the x direction. So that was the confusion there. If that ended up being a big issue for you, please just send me a message so that I know what's going on, and I'll be happy to give you a little bit of grace or extend the assignment or something. So just talk to me. All right. I understand that there was some confusion, and I totally understand why there was confusion. I don't want that to be a problem for folks. So just talk to me if it was. All right. Anyway, other than that, are there any homework questions or things you want to look at?
I was just kind of curious about, I noticed that we have 2.6 through 2.9 all due on Monday for homework. Are we going to be going over 2.9 as well?
No, I will adjust that as well. We're a little bit behind, and you may have noticed that for the last couple of weeks I've been pulling one and throwing it in the future. Same thing's going to happen with 2.9. All right. And it might even include 2.8. We'll see how I'm feeling by the end of the day. All right. Anything else? That was a good question. Thanks, Ricky. Thanks for reminding me to look at that. All right. Well, hearing nothing else, then I'm going to hop up to the whiteboard and we'll keep talking centers of mass. All right. So last time we looked at center of mass of a region that had sort of a funky top, but still had a nice straight bottom. And we saw that the idea was very much like what we did before. We cut the region into strips. We found the center of mass of each strip, and then found the moments and everything else. Well, we're going to do the same thing today, but now instead of just having one function that defines this region, we're going to have two. All right, so maybe we've got a shape that looks like this. So we'll call those functions f and g, f for the top one, g for the bottom. All right, so the idea, just like before, is to see if we can figure out center of mass. So when we find center of mass, there are three things we have to find. One is the mass of the object itself. The other two are the moments about the two axes, so my and mx. But for all of those, we're going to approach it in the same way, which is we're going to start by dividing this into a bunch of strips. So let's put a little representative slice here. So if we start with just the mass, in order to find the mass of this object, we need to find the mass of that strip and add it to the masses of all the other strips. Make the strip smaller, so we have an infinite number of them, blah, 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 right? And so that's going to end up giving us an integral, just like we've seen many times before. But the mass of this thing is going to be an integral from a to b. All those guys, a and b, the bounds, the horizontal bounds of this region. And what we're going to have in here is our density times area. Right? It's always density times area. But for that rectangle, for its area, we need height times width. Its height is going to be f of x minus g of x. And then its width is going to be dx. All right. So again, all this is height. And this is the width. So I just want you to notice the only difference now, as opposed to the example we did last time, which was just a function on top, is that we're subtracting the bottom function now, because we don't want the entire height from the axis to f. We just want the height between f and g. And it's the same idea as finding the area between curves, right? It's just we've got a density in here now. All right, so there's the mass, and it's pretty easy. It's very little change. But the other ones are going to look a little bit different. The finding of the moments. So again, we need to know where the center of mass of this little strip is. But if the density is constant, we know we can go straight to the middle of this. And so this point is going to be the point, we call it xi, for the height rectangle. But now we need the point that's exactly halfway in between f and g. So that's the average. And that ends up being f of xi plus g of xi over 2. So that's the y coordinate of that point. So now with those, we can go ahead and build the other moments. All right, so for the other moments, what we need to know how far away this point is from the axis, whichever one, and then we multiply it by the mass, which is going to be the mass of this strip. All right, so let's build these guys. I've got over here, why not? So let's start with the my. So this is the moment about the y-axis. So we're going to integrate again from a to b. So let's think about what's going to go in here. I need to multiply the distance the strip is away from the y-axis. Well, that's going to be my x-coordinate. And then I need to multiply that by the weight of this strip. Well, the mass of this strip was actually this guy. So all we're going to do is take the same thing, but put an x in here. So this is going to be rho x times f of x minus g of x dx. And if you go back and you look at the one that we did before, again, the only difference is now we're subtracting g of x. That wasn't in there before because it didn't have anything to do with, there was no g of x, and it didn't affect the mass. So there's the my. Again, virtually the same as the one before. But the mx is going to look a little bit different. If we go to mx, again, we're going to integrate from a to b. We want to take the distance that this point is from the x-axis. That's going to be its y-coordinate. And we want to multiply by its mass. So that's going to give us, the mass was rho times f of x minus g of x. But now we need to multiply that by f of x plus g of x over 2. Because that was the y-coordinate of this thing. So we're going to do a little bit of algebra. If we distribute, we're going to get the 1/2 rho, but then the others are a difference of squares. So we get f of x squared minus g of x squared. So that one definitely looks different than what we saw before, when it was just a function on top. But they're all derived exactly the same way. They're all derived the way that the others were. We're just using the fact that the strip is between f and g. So, because I know you all want boxes, this one, the purple one, is how we find the mass. The black one is how we find the my. The red one is how we find the mx. And so for the center of mass, remember what we do is we just take the corresponding moments and divide by the mass. So virtually the same as what we did before. All right, so we've done all the work, really. We've developed the formulas. And so now it's just going to be plug them in and go. All right, so let's do an example here. Let's take actually a region that has constant density. So it turns out the densities aren't going to matter. But we're going to see if we can calculate the center of mass. So this one, let's find the center of mass. Of the region bounded by y equals x and y equals x squared. That's probably my favorite region that's bounded by functions. We tend to run into it a lot. But let's see if we can figure out where the center of mass is. So let's start with drawing a graph of it, just so we know what we're doing. Y equals x, of course, that's the line that goes through the origin with the slope of 1. So that looks like this. And then y equals x squared is a parabola, vertex at the origin. So there's our region. And we want to figure out where its center of mass is. All right. So before we get going too far, let's think about what the bounds are going to be for this. Obviously, these come together at the origin, so that's going to be at x equals 0. Where's this other point? Where's the other point that those come together?
1.
There you go, at x equals 1. If you just take x instead of equal to x squared, it's x equals 1. Okay, so all of our bounds on all of these things are going to be 0 to 1. 0 to 1, 0 to 1, 0 to 1. All right, so let's go ahead and start with mass. I'm about to erase the formula, but we'll redo it here. So the mass of this thing is going to be the integral from 0 to 1 rho times the difference in the functions, so x minus x squared dx. All right, well, that's an easy enough one to do. X squared over 2 minus x cubed over 3, right? 0 to 1. Pull the row out front. Oops. Actually do the integral. Rho times x squared over 2 minus x cubed over 3 from 0 to 1 gives you 1/6. So we got rho over 6. So if you know what the density is, divide it by 6, and that's the mass of that. All right, cool. First step. Okay, second step. Let's calculate the my. All right, so we're gonna use this formula up here. My, we're gonna integrate from 0 to 1. Rho times x minus x squared. So that's the integral from 0 to 1 of rho times x squared minus x cubed. And that one's also nice and quick. We pull the row out front. X cubed over 3 minus x to the 4th over 4 from 0 to 1. And that gives us 1/12. So the my is rho over 12. So again, you tell me what the density is. I divide it by 12, and that's the moment about the y-axis. All right, well, that leaves us then mx. So mx, the integral from 0 to 1 of 1/2 rho times the difference of squares of the two functions. So we're going to have x squared minus x squared squared. And that just came from the derivation for center of mass. Okay, so that's 1/2 rho times the integral of x squared minus x to the 4th. All right, so that's 1/2 rho times x cubed over 3 minus x to the 5th over 5. And that ends up giving us rho over 15. All right, so like I said, at this point, it's just go through the motions, go through the motions, go through the motions. All right, so now we're ready to get the center of mass. So I'm gonna erase this bit, but let's just remember that the mass is rho over 6 here. All right, so here we go. Let's get the center of mass. So we've got x bar. That's going to equal that my over the mass. So that's rho over 12 divided by rho over 6. If you flip it and multiply, you end up getting 1/2. So that's the x coordinate of our center of mass. All right, so then for y coordinate, y bar is going to be mx over the mass. So that's going to be rho over 15 divided by rho over 6. Again, if you flip it and multiply, that reduces down to 2/5. So our center of mass is going to be right around here, where the x coordinate is 1/2 and the y coordinate is 2/5. All right, so again, the process isn't different. Process is exactly the same. We just end up getting a different formula for the mx, the my, and mass and stuff like that, because of the fact that we're looking between two surfaces or two functions. All right, so hopefully you can see how this plays out. Obviously, what's going to make it difficult is the functions themselves, because that can make these look like whatever. It just turned out that these were nice. They were just polynomials, but whatever. It is what it is. You integrate what you end up getting. This is where they have to come in. So I had someone send me an email and say, is this stuff going to matter in later math classes? And I just put a tone on there that it wasn't tone like that. But that's the legit question, right? Where you go, okay, I'm not a physicist. I don't care about this. Whatever. Well, you're still going to see this again in Mat107. You're just going to extend it to bigger, weirder things and develop some other ways of calculating that are maybe even a little bit easier using these things called double integrals. So just be aware that center of mass stuff is not going away. You will see it again, even if you just take calculus. All right, but I wanted to show you one of these because it is a little bit more complicated, but it's still not that. All right, so questions on this one? All good? All right, so the next set of applications I want to show you are things that have to deal with exponentials. And specifically, we're going to look at exponential growth and exponential decay.
I have a question really fast, sorry.
Yeah.
If they
that's
give
cool.
you the density, do you have to do all of it, or is there like a shortcut since they already gave it to you? Because in a bunch of the homework problems, they like give you the density.
Okay, so it depends what they're asking. Well, and it also depends what the density looks like. So this is kind of a deeper question, but let's start with constant density. All right, so let's say the density is constant. They just say, hey, the density is 5, kilograms per cubic meter or whatever. Okay, if it's constant, when it comes to the center of mass, density doesn't matter. It always cancels out. If the density isn't constant, so it depends on x, then you have to include that when you do your integral, right? Because like think about just the mass example, it was density times f minus g. So if that density depends on x, you have to take that function times f minus g before you integrate. And then the same thing for the two moments. If what you're looking for is just mass, then definitely you need the density because there isn't anything for it to cancel out with, right? The reason the density canceled out with the center of mass is because we were dividing and each of those things had a density in it, so you could, cross them out. But if all you're doing is just finding the mass, then you definitely need the density still in there. Or if you're just finding the moment about the x-axis or the moment about the y-axis, you don't usually just find those things. Those are usually used to then get the center of mass. So the short answer is it depends. But the longer answer is notice if it's constant density versus non-constant density, and then what specifically are you looking for? Center of mass, you don't have to worry about density if it's constant. Mass, you do have to worry about the density even if it's constant. So does that kind of answer your question there, Alexi?
Yeah, thank you.
Okay, you're welcome. Okay, so the next set of applications, like I said, I want to look at exponential growth and decay. Now, you have probably seen this before in a non-calculus class, right? We usually talk about this in pre-calculus as an example of where we care about exponents and logs and stuff like that. But I want to show you where this comes from in terms of calculus. Like, why are we seeing this again? So exponential growth and decay, you may recall that what this looks like, or the equation for this, was one that looked like y equals CE to the KT. It comes in all kinds of different forms. You might know it as PE to the RT, AE to the KT. I mean, there's all kinds of names for this. But this is a typical exponential growth or decay function. The difference between growth and decay, do you remember what in here tells you if it's growth or decay?
The K value?
Yeah, it's all about the K. So this guy is what will determine if it's growth or decay. It's growth when K is greater than 0, and it's decay when K is less than 0. And that just comes from looking at the graphs of exponentials. If we have e to a positive power, it's an exponential function that goes up, so it grows. If K is negative, that's a reflection, and so then that function decays. All right, so the K will tell you whether it grows or decays. And because of that, this K, its name is actually it's either the growth rate or the decay rate. So I just call it the growth rate, thinking that decay is negative growth. That's how I think about it in my mind. All right, so in terms of applications, this is actually a big deal, finding out what K is. Because if you know how quickly something grows or decays, then you're going to be able to model what happens later. All right. So more review quiz for class. Does anybody remember what the C is, or what the C tells you?
Your starting value, like your kind of constant, or like if it's money, it's like how much you've originally deposited.
Yep, good. So if it's like a money example, you're right, Susanna. That's we call it the principal, and it's how much you're starting with. But we'll just say it's the initial amount. So if we're doing a decay thing, it's the initial amount of this radioactive isotope. If we're talking about, you know, a population growing, it's the initial amount of kokanee in the lake, or, you know, whatever, right? So that C is always the initial amount. Y equals CE KT. Now, the reason that's your initial amount is if you were to plug 0 in for T, we get e to the 0, which is 1. And so that's what we're left with. All right, so this is all algebra stuff. I mean, you've learned about this in algebra, but let me show you where this comes about from calculus and how calculus is related to this. So the first thing I want to do is differentiate y. I just want to differentiate y. So if y is equal to CE to the KT, let's find dy dt. All right, so C is a constant multiple. It's going to stick around. Then we have e to the KT. So we know the derivative of e to the something is that e to the something. But then we have to use the chain rule. We have to differentiate that exponent. And if we differentiate that with respect to t, we get decay. All right, so the c showed up again because it's constant multiple. The e to the stuff shows up because that's how you differentiate e to the stuff. And then the k is the derivative of the stuff. All right, but check this out. That ce to the kt, that was what we started with. That's just y. So it turns out that with exponential growth and decay, what we have here is y prime equals k times y. All right, so fun fact, the derivative of something that follows exponential growth is just a multiple of that original function. And in fact, it's the growth rate times that. Well, in words, what this means, this is just saying that the rate of change is proportional to the, and I'm going to put here, population. And it literally can be population if we're going to talk about counting the number of people or critters. But when I say population, that could also mean the amount of our radioactive isotope, the amount of money in our account. Okay, but basically, this is just saying that the rate of change depends on how much you have. The greater amount that you have, the faster it's going to change. You know that old adage, it takes money to make money? That's exactly what this is saying. The more money you have, the faster it's going to change. So the more money you have, the faster it grows, right? That's why if you're a billionaire, you'll be a billionaire forever. Because it's just going to grow really quickly. All right, well, this is what the calculus shows you, that this is such that the rate of change is proportional to the population. And in fact, you could take this and go backwards and see why this equation with the y prime forces exponential growth. So I just want to show you this real quick. Check this out. This is kind of an aside, but if we were to do this dy dt equals k times y, what I'm going to do is a little bit of algebra. I'm just going to move some things around here. So I have dy over y is equal to k times dt. So I just kind of shifted things around. But now, let's integrate both of these sides. So let's think about the left. What do you get when you integrate dy over y? You've seen that form before. What does that give you? All right, good. It's natural log. Thanks, Adam. So this is going to be the natural log of y. If we go to the other side, k, it's a constant. And if we integrate dt, we get t. So we get natural log of y equals e to the kt. Now, we should be good about it and put a plus c. Technically, I should put a plus c on both sides, but I can move the one over to the other side and make it yet another arbitrary constant. And now if I want to get rid of that natural log, I can convert this into an exponential. So I'm going to get y is equal to e to the kt plus c. The rules of exponents tell me I can write it like that. I can split it apart since there's addition as an exponent. It's multiplication of the two separate things. And then this e to the c, since c is an arbitrary constant, so is e to the c. I'll rename it to a just to make you feel a little bit better. But notice that, yep, it leads to the same exponential growth. So that's a key phrase you're going to want to look for. If you see something that says the rate of change in this quantity is proportional to the amount of the quantity, like that, that's a trigger. That should be a trigger that goes, ooh, this is exponential growth. Okay. So there's your first little connection back to calculus, is that these things, the growth rate is proportional to the population. Decay rate, you can always replace that for growth rate. Okay, so let's just look at some specific examples just to remind ourselves how we play around with exponential things. We'll do a couple of growths, we'll do a couple of decays, just so you can see them. All right, so let's just start with a nice simple example. It's kind of a classic example. Let's say we have a petri dish filled with bacteria. All right, so we're going to start with 500 bacteria. I think it's technically bacterium. I'm not a biologist, but I do know a little Latin. So we're going to start with 500 bacterium. All right, after 3 hours, there are 8,000 bacterium are present. All right, so now my question is, let's do this. Let's find the growth constant. And then let's figure out how many we'll have in 10 hours. Okay, so it's a two-part question. We want to figure out the growth rate, the growth constant. Okay. And then we want to figure out how many there are going to be in 10 hours. All right, so here's what we're going to do. Let's go back to the y equals CE to the KT. And let's start building this equation. So first thing, we know that we started with 500. So that's going to tell me that C is equal to 500. Awesome. So now that still doesn't help us find K directly, but we also know another combination of Y and T. Right? We've got this after 3 hours, there are 8,000 bacteria present. So this is Y equals 8,000 when T is equal to 3. So we can actually put those in here. And that's an equation that we can solve for K. So let's do that. See, that's the first part of this question is what's the growth constant? So let me rewrite that up here. We got 8,000 equals 500 e to the 3k. So I'm going to start by dividing by 500. So we're going to get 16 is equal to 3k. And to solve for that k, we're going to take a natural log. So we'll get the natural log of 16 equals 3k, or k is the natural log of 16 divided by 3. So that's the exact value for k. At this point, it's fine to go ahead and get a decimal approximation. I'm going to imagine that any of these homework problems are going to ask you to put this in as a decimal, rounded to some number of decimal places. So we'll call it good. But this one, I got a value k is 0.9242. So that's the growth constant for this bacteria, 0.9242. It's positive, which it must be because we're growing. So that means that our equation then looks like y equals 500 times e to the 0.9242 t. And we can now use that to model this bacteria growth and have an idea of how many we're going to have at any different point in time. So for the second part, where it's how many are in 10, do we have in 10 hours? We plug in 10 for our t, 500 e to the 0.9242 times 10. So again, this is a calculator question. So let's see what we get. So I have 500 times e, that times 10.
I got 5160830.625.
All right, I get a very similar number. Let's see. So we'll round to the, I'll round to the nearest whole number. So 516.0637, and mine is maybe a little bit different because I actually kept more decimal places, but it should be on the same order, right? So check it out. In 10 hours, they're going to be over 5 million of these cells. Holy crap, that grows fast, right? In 3 hours, we'd already gone up to 8,000. By the time we get to 10 hours, we're at 5 million. Well, exponential growth works that way. It grows very quickly, right? Because its growth rate is proportional to how much is there. All right, anyway, so there's your kind of typical exponential growth problem. Again, it's very algebra-y, but there's some calculus behind it, right? And in fact, when you were first taught, oh, we use exponential functions to talk about exponential growth, it was kind of cart before the horse kind of deal. The calculus is why you can do that, but we teach it to you in pre-calculus so you can play with the rules of logs and exponents. All right, so here's an example with bacteria. Here's another example that has to do with money. Because money also follows exponential growth when we use compound interest. And this is continuously compounded interest. So this is compound interest is interest earns interest. And continuously just means what it sounds like. It's always happening. When we talk about like a bank account or the amount you owe on a loan or something like that, continuously compounded doesn't make sense. But for things like inflation, the economy, the growth of the stock market and stuff like that in the long term, then yes, we can do continuously compounded. So it's sort of a theoretical and yet can be used. And again, it's an exponential deal here. I'm going to change the letters a little bit because this is what we usually see for compound interest. I call it the Pert formula. But all the pieces are still the same. This guy P, that's our initial amount. And that's what we call the principal. I'm not sure which principal it is. I'm going to go with principal. I'll just go with the 50-50. But this is the initial amount. So it could be the initial amount that you invest, the $500 you put into the checking account. Or it can be the initial amount of a loan. And, oh, I took out a $5,000 car loan, whatever. Okay, that's your initial amount. And then R is your growth rate. But in this context, this is our interest rate. It's our 5% per year, 12% annual, whatever it happens to be. But it still follows exponential growth. All right, so let's just do this. Suppose you want $1 million. And you want this in 10 years. Because you're thinking to yourself, all right, so if I can get $1 million in 10 years, I'll be set. Life will be good. All right, here's my question. How much do you need to invest now to get that if you can earn 5%? Okay, and we're going to assume that this is continuously compounded 5%. So let's just see what that number is. Let's see how much we'd have to put away right now so that in 10 years we'd have $1 million. All right, so let's think about this formula and think about all the different things we know and all that. So we want $1 million in 10 years. That's A. Right? That's our $1 million is our A. The 10 years is our T. The 5% is our growth rate. And how much we need now, well, that's our P. So we actually know everything in here but P. So let's put that all in. So we want $1 million. Don't know what P is. I know my interest rate is 0.05. And I know I want that in 10 years. So P is going to be 1 million divided by E to the 0.5. All right, so again, this is a good old calculator question. And I end up with 606, 530, and 66 cents. In general, it's a good idea if you're doing money problems to just round them to the nearest penny. All right, but there you go. That's how much we'd have to invest right now. Have $1 million in 10 years. So I know that seems like a big number. I mean, and it is. I don't think any of us have a spare 600 grand to just drop into an account to earn some money. If you do, let's talk after class. I have better ways for you to invest your money. I don't. All right, so 606,000. It seems like a lot, but I want you to realize this. Look at what happened in 10 years. We gained $400,000. Right, $400,000 in 10 years. Just by letting it go. That's 2/3 of what we started with. Right? So this actually grows quite quickly. In fact, let's do this. Let's look and see how long it takes to double our money. Because it's going to be a little bit more than 10. Right? A little bit more than 10 years. Because we didn't quite double, but let's just see what happens. So Bruno's throwing out his appeal for BitConnect. I don't trust virtual currency personally, but more power to you. All right, well, let's see what happens if we are still doing 5%. Let's see how long it takes to double it. All right, so here's the follow-up question. How long until we double our investment at 5%? Okay, so how long until we double our investment at 5%? I was not aware of the meme. I'll have to look that up. But I can just imagine what Dogecoin looks like. Oh, the Doge Shiba Inu. I have a Shiba Inu. She's a little pain in the ass dog, but it's kind of funny because sometimes I'm like, that's my dog. Anyway, all right, so how long until we double our investment? So you might be thinking to yourself, it depends how much we start with, right? If I put in $500,000 versus $100, I'm going to double faster if I have more money. But it turns out it doesn't. Check this out. So here's what I'm going to do. I'm going to leave my initial amount as just P. But if I were to double it, I'm looking for when does P become 2P? So when does $100 become $200? When does $500,000 become 1 million? And so on. And I want to solve this for time, right? Let me put in my interest rate as well. So we've got 2P equals PE to the 0.05 times T. Well, the first thing I'm going to do to try to solve this is I'm going to divide by P. And when I divide by P, notice that it cancels on both sides. So immediately it turns out it doesn't matter what our principal was. So this is a weird thing. Like it doesn't seem intuitive, but it's absolutely true. It doesn't matter how much you start with. We want to find out the amount of time it's going to take to double. All right, well, take a natural log of both sides. We can divide by the 0.05. And now we're ready to get our doubling time. So we'll take the natural log of 2, divide it by 0.05. I'm having one of those days. All right, and I get 13.86. And this is in years. So we're actually going to double in just under 14 years. And again, it doesn't matter how much we start with. So you put $1,000 into the bank, earning 5% interest. In 13.86 years, you'll be up to $2,000. If you put $1 million in there right now at 5%, in 13.86 years, you'll have $2 million. So we're still doubling the same amount of time, but obviously the other one is better. You just made $1 million over 13 some years as opposed to $1,000. So the actual amounts depends on how much you're starting with, but the amount of time it takes to double is always going to be the same. So there's a little bit about continuously compounding. I just noticed that we're out of time. It's like, oh, it's starting to get light out here. Remember, I'm in Hawaii, so it's a 2-hour difference. So it's like 8 in the morning right now. So we're out of time. I didn't get to show you any decay. So on Monday, I'll show you some exponential decay. We'll talk about half-lives, which is similar to doubling time. And then I'll show you another cool application. I think it's cool, Newton's law of cooling. And then after that, we will look at these things called hyperbolic functions. So in terms of the homeworks, I'm definitely going to move 2.9. I think is the one on hyperbolic functions. That one we're going to put forward. I think I'm going to keep the exponential growth and decay one on there because you can do all of the exponential growth stuff, and I bet you can do most of the exponential decay because it's the same math. It's just to get negative k's. So we'll leave that as something to do on Monday night, which I'll be willing to reassess that on Monday morning. All right. Okay, so I guess with that, we will call it a day. Have an awesome weekend, and I will see you all on Monday.